But wasn't all there.
Yeah, I've quite asked you this before, but I'll ask it. How many of you have encountered in your travels vectors in a math class or any other class? You've seen a little bit of it. What we're going to do for the next little bit is talk about vectors. Yesterday, well, the last time we met, we found solutions to a system of linear equations, and I wrote the answers as a vector. A vector is just I usually write my vectors as columns, but you can write them as rows as well. It's just an ordered list of entries. So a vector, another way to put it, uh, let me call this an n vector, is an ordered list of n real numbers, or perhaps complex numbers, if I'm doing something later. But it's something of this form. Another way to put this is an n by one matrix. We talked about augmented matrices. An augmented matrix is just like an array or a table, right, of numbers. This has n rows and one column, right? So another way to think of a vector is just a very skinny matrix. For example, you might have had some experience. Some of you may have had Calc 3, or maybe even in Calc 2, you've done a little bit. So, for example, 2, 1 minus 3 is a 3 vector. 3, 4 is a 2 vector. And you can actually think of this as being represented in plane. Let's see if I can do this right. 4. So over 3 up 4. So sometimes people, physicists love to do this, write the vector as an arrow, right? But really the key thing is the head of this is at the point x equals 3, y equals 4, right? Right, okay. So the n vector, in more generality, has n entries in it, right, corresponding to n-dimensional space. And you may think that I'm making this up past dimension 3, but I'm not, because there's lots of things, for example, in robotics, when you have a robot that you're building that has lots of degrees of freedom for its various appendages, its arms and its legs, you might need a 10-dimensional vector to represent everything that's going on, for example. Right. But another way to think of this, sometimes we say this vector has n dimensions because that's the number of parameters it takes to tell me what the vector is. I need n numbers to tell me exactly what it is. So in particular, we say, so let me introduce that U and V So when you see this notation right here, this means U and V are n vectors, or n by one matrices, elements of Rn, are equal if and only if they have the same entries. In order. Right. That is to say, A1, A2, AN is equal to B1, B2, BN. If and only if A1 equals B1, A2 equals B2, all the way down to AN. This is how we say two vectors are equal if all their components match. Okay. One of the things about vectors that's very useful is vectors actually have some structure to them. How many of you have seen maybe in a dynamics class or an engineering class where they took two vectors like this and added them up? Have I ever seen it? Anybody remember how did they tell you to add up vectors? Anybody remember? Yeah.
You put the tail of one on the head of the other.
Right, the head to tail thing. How many of you have you ever heard of the parallelogram law? I'm gonna write that down in a bit, right? And in fact, if this vector here is 3, 4, and let's see if I drew this one right, this would be get my 3, it's not very good. Make it better, 3, 4. There you go. And this vector right here is 3, 1. My geometry is not so good, but so bear with me. If I draw a parallel line here, that is parallel to this vector, and then one that's parallel to this one, the resulting vector here should be what it is. And if I had drawn this right, anybody know what this vector has to be?
5.
That's what it looks like, but you're not factoring in the fact that I'm a crappy drawer. It's actually 6, 5. Oh, maybe you meant the second chord. Yeah.
I'm looking at the wrong numbers. I thought.
So you basically, the way you add vectors is just component by component, right? So you can't beat that with a stick. So, so the way you add A1, A2 up to AN plus B1, B2 up to BN. By the way, you can only add two vectors if they're the same size. You can't add a 3-dimensional vector and a 2-dimensional vector. You'd have to take the 2-dimensional vector and make it 3-dimensional somehow. But you have to have it matching up. You do this, I think, in sort of the easiest way possible, I hope. And that is just to add vectors, you got to just coordinate this. Anybody okay? Anybody know what else you can do with vectors that's kind of a common thing? So you can take two vectors and add them. What else can you do? Yeah.
Dot product.
Yes, we're going to get to that later. But what I want to do, there's another way that you can sort of multiply something and also get a vector. Because when you take the dot product, you get a number. Right, but that's only for 3-dimensional vectors. I'm looking at something more simple. You can also scale a vector, right? You can multiply it by a real number. You can make it grow. You can make it contract. You can make it 0. You can multiply it by 0 if you like, right? You can also scale by a constant. C and the roots. Remember, that simply means real number. So, in other words, if you multiply a constant times A1, A2, AN, it just stretches all the components or contracts them by C. Second. let me do a kind of a numerical example. So what would happen if I did something like this? 2.04 D equals 113 minus 7, and W equals minus 2 minus 1, 4. Now, suppose I wanted to put these together in some fancy way. So let's do 2U minus 3V plus 5W. So I'm doing it kind of all together. I'm scaling them and I'm adding them up. Right? Let's do this piece by piece. Okay, when I multiply U by 2, I should get 4208, right? I'm going to write plus here because me having parents that are cousins and all, I always get confused about the minus sign. So I'm going to go ahead and put that minus 3 already in there to kind of cover myself. And so minus 3 times B is minus 3 minus 3 minus 9, 21. Everybody okay with that? And 5W minus 10 minus 5, 20, 15. Right? And now all I got to do is just put all the stuff together. And let's see here. What's that across the top? That's going to be minus 9, isn't it? This one is going to be 2 minus 8 is minus 6. 0 minus 9 plus 20 is 11. And 29 and 15 is 40. So that is the new vector I would get by combining these. That way, okay? Okay. I'm going to, I sort of wrote this down in a sloppy way, but I'm gonna write this down more carefully here. So geometrically, you add vectors via the parallelogram. Which is equivalent to the head to tail thing that you spoke of as well. And what the parallelogram law says is, I'm just kind of going to draw it for you. If you have, say, vector U and vector V, then to get U plus V, you just kind of take the resultant parallelogram. Let me try to draw this as best I can. Okay, so that's supposed to be parallel to this, and this is supposed to be parallel to this. So here's my parallelogram, and I did that right. And you can actually do a computation and show this works. Now, let me point out that you may think, well, it's pretty specialized, right? Because you need a plane, right? You need only 2 dimensions. However, let me point out that if I take any 2 vectors, just take this U and V, which sit in 4-dimensional space. Now, it's hard for me to draw 4 coordinates there, but wherever this vector lives, and this vector lives, those 2 vectors by themselves, what do they form?
Plane.
That's exactly, well, maybe. These two vectors by themselves in four-dimensional space, this is going one direction, this is going possibly another. It's going to look just like this if you only look at these two vectors. And why did I say maybe a plane?
If they form a line.
That's right. It could be the case that these two vectors right here lie on the same line, right? In which case, so they'll form at most a plane, or maybe it'll just be a line. Space. By the way, these two vectors, U and V, how many do you think they form a line? How many do you think they form a plane instead? You are correct. Well, the youth today need to get out and vote more. Anybody, why is it that they form a plane and not just a line? Does anybody know why?
Multiples.
That's right. We're going to get to this. We're going to get to this later, but for this to just to form a line, these two vectors would have to be parallel in some sense, right? And what we're going to see later is that means that this one has to be a multiple of this one, right? Is this vector a scalar multiple of this, or vice versa? Well, any scalar multiple of this has to have 0 in the third coordinate, doesn't it? No way, right? So these actually do form a plane. Okay, any questions on that? Question. Okay, so let me give you some properties here of this vector addition. So here's and in this little theorem, I'm going to introduce a notation too. And C D. Okay, so you're learning a little bit of the new language here. Let me tell you what this means. All this means U, V, and W in Rn. This just means these are n vectors. They require n entries, and those entries come from the real numbers, right? So these are just n-dimensional real vectors. And the C and D right there, C and D and R, that just means C and D are numbers, period. So let's look at some of those properties. And a lot of these will make you laugh and scoff at me because some of these properties will be kind of obvious that they're true. First property. This is often called commutativity. This means it doesn't matter what order you add the vectors in, right? U plus V, V plus U, same animal. And if you think about the way you add vectors, this makes sense, doesn't it? Because you just add them just by adding the entries, right? The first coordinate of the sum of these is 3, and it doesn't matter if it's 2 plus 1 or 1 plus 2, right? Two. This is called associativity. If you're adding more than 2 vectors, it doesn't matter which 2 you combine first. That is, U plus V plus W is the same thing as U plus V plus W. Doesn't matter which 2 you put together first, it all comes out in the wash. What do I mean by 0 with a hat on it? This is called the 0 vector. It's the vector filled with zeros. What happens when you add the 0 vector to any vector? What do you suppose happens? Nothing. That's right, it leaves it alone, doesn't it? 4. I'm going to define negative u to be -1 times the vector u. So basically, negative u is the vector where I've changed all the signs of u, just reversed them all. What happens if I do this? What should I get?
Zero vector.
I should get the 0 vector. Good. Here's one that says that I can do two things to vectors, right? I can add them and I can scale them. This next one says scaling and adding play nice together. If I scale the vector u plus v, what do you suppose this should be?
C plus C.
That's right. You scale u, add it to scale v. So scaling and addition are compatible. It's also compatible from the other perspective. If I have two numbers, c and d, c plus d times u is cu plus du. Also, I've got sort of an associativity. If I have cd times vector u, this is the same thing as c times the vector du. And finally, this can be proved by our definitions, but in more general structures, you actually kind of need this. This almost seems like, why, Jim, have you lost your mind? Why are you writing this down? Because actually, like I said, in a more general setting, this is actually important. When I multiply, when I scale any vector by 1, I get the vector back. 1 times any vector is the vector itself. Okay. Let me make a kind of a connection here. Any questions? Move on. Let me give you another definition that we're going to see this come up quite frequently. Suppose that I walked up to you on the street and give you a collection of vectors. Okay, so this is any collection of vectors. Actually, it can also be an infinite set, but we're going to start just right here. We just assume that I'm only finite many vectors. The span of V1, V2, Vn is the collection of all linear combinations of the vectors V1 up to Vn. So when I say the span of this set of vectors V1 up to Vn, it is just every linear combination. What do I mean by a linear combination? So let me put this another way. Is every possible vector of form C1 V1 plus C2 V2 plus Cn Vn, where C1, C2, Cn are written like this. So
Use
the,
the notation on the top.
I'm sorry.
It went to VM and then you changed it. to
Oh,
VM.
yeah, you're right. The easiest thing is for me to change that to the end. Yeah, that's right. Thank you for catching that. So what it means to be in the span is every freaking linear combination of those vectors. Let me kind of get my feet wet by thinking about this. Can anybody name any vector that for sure is going to be in the span? Any specific vector?
Zero.
I like that. The smart aleck answer is always the best answer to start with. What you could do is you could take every one of these C's to be zero, right? So no matter how you cut this cake, the zero vector is always going to be in the span. Everybody agree with that? Also note that V1 is in the span. You could just take C1 to be 1 and the rest of them to be 0. C2 is in the span. You could take C2 to be 1 and the rest to be 0. And so 7V1 plus 12V2 minus 14Vn is in the span. It's everything you can think of. This is just what the span is. And this actually, we're going to look at this later. This actually forms what we call a vector space. And these are important objects of application for you all in your near future. So, right. So any questions on it? Let me show you kind of a connection, right? I mean, some of you may think that, I've had a stroke and all of a sudden, after talking about this linear equation, I start talking about vectors. But there's a connection here, right? So suppose I gave you this this equation here. So let's let U equal minus 214. V equal 103. And B equal minus 3 to LF, right? Now I can write a vector equation as follows. I could say, can we solve this equation here for x1 and x? Can we find values of x1 and x2 that balance this equation? Well, let's just kind of go through this. We're not necessarily going to answer this question or solve it, but let's go through how we might tackle this problem. Can I solve this vector? Well, let me rewrite this as it is, what it is. It's x1 times minus 214 plus x2 times 103 equals whatever b was, which was minus 3 to 11. Right? Now, that left side up there looks a little busy to me, so I'm going to try to make that a little cleaner. Right? That's just basically pushing those scales inside there. All right, the x1 inside the first one. And let me once again rewrite this. This right here, I can write this as a single vector on the left side. This is 2x1 minus 2x1 plus x2 x1 and 4x1 plus 3x2. And this is equal to minus 3 to 11, right? Now, what does it mean for two vectors, left and right there, to be the same? Well, it means that all their components have to match. And what do I get out of this? Well, what I get is a system of linear equations, and that's one of the big connections. Basically, what I would get from this are the equations minus 2x1 plus x2 is minus 3. X1 is equal to 2. And 4x1 plus 3x2 is equal to 11. I can solve this equation for appropriate values of x1 and x2 if and only if that system of three linear equations is a consistent system. And so that's actually one of the big connections here. Let me ask you another question here. On let me ask you a question. What do you think here? Suppose I give you vectors here. So U is probably going to be like that, and V is going to be like, actually, let's keep this. Right. 1 minus. Everybody read these two vectors in one unit, right? Anybody want to guess what is the span?
The area inside of it.
Well, certainly you could get that, right? But can't you also make V longer and longer and longer? And actually, you can make V go the other way too. You make V go that way. How can you do that? Right, you can multiply by a negative number and shoot it off that way. Anybody want to guess what the span of these two vectors is? Yeah.
The plane.
It is the entire R2, right? You give me any vector in R2, and I can find you appropriate any vector, this one. Z. I can find an appropriate thing to multiply U and V by. It'll give me Z. That's probably not clear, is it? Right? But I bet we can. Let's actually test this. Probably good. Somebody give me, I've given specific values for U and V. Somebody give me a Z. It doesn't even have to point in that direction. Somebody give me 2 coordinates.
-7.3.
Right. Well, my question is, can we get x1 times 2,1 plus 2,1, wasn't it? Plus x2 times 1 minus 1 is equal to 7,3. I'm sorry, minus 7, right? Well, just like we did before, this is basically the vector 2x1 plus x2, x1 minus x2. Everybody agree with that? So I get 2x1 plus x2 minus 7, and x1 minus x2 is 3. Everybody okay with that? Let's look at the augmented matrix, all that fun stuff we did last time. 2, 1, minus 7, 1, minus 1, 3. And you know what? I'm gonna up the voltage here. Forget 7 and 3. How about 8? 8, right? So I'm not just doing the problem that was given to me with the minus 7 and 3. Now I'm doing it for anything. In the special case today is minus 7, B is 3. We can solve that problem here. Are you okay with it? Okay. I like ones. So I'm going to do this. Okay. All I did is just flip. I'm going to multiply this by -2. Take this out. And I'm going to get 1 minus 1 B. That's going to be 0. Multiply this by -2, that's going to be 3, that's going to be 4. That's going to be A minus 2B. Everybody agree with my assessment there? I don't. What I multiply this by -2, and here I get 0, -2, that's going to be 3, not 4. And that's going, yeah, it looks right. Everybody okay with this? So this gives me easier equations. So x2, A minus 2B over 3. And once I know that, I've got it licked, because x1 is x2 plus b, which is a minus 2b over 3 plus b, which is a plus b over 3. So with the -7, 3 that we had before, that would be, my x1 would have to be, I guess, -4/3, and my x2 would have to be, I guess, -13/3. Right? But doesn't matter. Everything's in the span. Everybody agree with that? Okay, any questions on that? Let me point this out here. The vector equation if I have the vector equation x1 a1, well, x1 u1 plus x2 u2 plus xn an or un equals b, this has the same solution set. That is the values for x1 up to xn, same solution set as the linear system with augmented matrix. U1, U2, UN. So in particular, B is a linear combination of U1, U2, UN, which is the same thing as saying in the span of these vectors. If and only if the system is consistent. Okay, any questions? Okay, with this, I want to examine. So there's a connection, as we said, between systems of linear equations and these vector equations, right? The vector notation is basically letting you take a system of equations, which is, remember what a system is, it's a collection of these linear equations. And the vector stuff allows you to turn that into a single equation for vectors, right? It's just a more compact way of writing it. Now suppose A, okay, this is new notation two. This means matrices with m rows, n columns. With entries. When I wrote RM, that's RM by one, those are just vectors. So now instead of vectors, instead of n by one, I got n by n. This is more general. So if you have right, if we have if I write A this way, each AI is a column. So m by one vector. So we'll use this notation a lot. What I've done is this is the matrix that's m rows and n columns. Here are the columns, 1, 2, all the way up to n. And each of these columns are m tall, right? So that accounts for the rows. Then we define, if we have x is equal to x1, x2, up to xn. So this is just a vector, right? So A is a matrix, its columns are A1 up to AN, and X is an n vector. Then we define let me kind of write this out. maybe it'll help us remember how it works. I'm gonna kind of show you a better computational way to do this as we evolve through this section. The way we define the multiplication, this matrix times this vector is first column times the first entry up here. So it is x1 column A1, and then the second entry times the second column, and so forth and so on. So you need the number of rows here. Notice this vector is in Rn. You need the number of rows here n to match the number of columns here, right? For this to make sense. So for example, let's do a concrete example. Let's do this. 1, 0, 2, 1 minus 1, 3 times the vector 2, 1, 5. Notice this vector, this matrix is 2 by 3, 2 rows by 3 columns, right? This vector here is, what is it? How many rows does the vector have?
3.
It's got 3 and only 1 column, right? So this is 3 by 1. Now, according to this rule, it should be 2 times the vector 1, 1, because that's the first column, plus 0, plus 1 times the second column, which is 0 minus 1, plus 5 times the third column, which is T3. So this is 2, 2 plus 0 minus 1 plus 10, 15. And so I get 12, 16, I guess. Okay, any questions on it? By the way, since we were talking about size and all, what's the size of this vector? How many rows?
2.
And 1 column. Notice this carries over more generally when we're multiplying matrices, and it's a good way to kind of keep your eye on the terrain, make sure you have it straight. For you to be able to multiply a matrix times vector, or more general, 2 matrices, this number and this number have to match, right? That's the only way it can be compatible. Everybody okay with that? And the output is what you get when you play accordion. Multiply by 3 by 1. And that's what we got. It's a 2 by 1 vector. Everybody okay with it? So that's a good, I think that's a good gut check to kind of keep your eye on there. Okay. Let me give you the last theorem here. Let A then AX equals B. Then this has the same solution as vector equation x1 a1 plus x to A2 plus x in AN equals B, which has same solution as system from augmented matrix A1, A2, AN. B. So AX equals B has solution if and only if B is in span of columns A. So this is kind of the last theorem for the day, and it ties together these kind of things that we've been talking about. So think about this and think about those connections, and we'll kind of tie up any loose ends next time and get on to section 5. Any questions? Questions? All right. Well, I will see you folks on Wednesday.